This lab tutorial is about load cell. Load cell is one type of transducer that is used to measure external force. Load cell typically is based on the principle of strain gauge. This picture on the left shows how the load cell looks like. This load cell includes 4 strain gauges that are composed of a full Wheatstone bridge. The 4 strain gauges composed of the full Wheatstone bridge are represented by those resistive components R1, R2, R3, R4 on the schematic. A Wheatstone bridge includes an excitation voltage applied across node A and node B, and the measurements are taken across node C and node D. If there's no load, all resistance are equal, and the output of the Wheatstone bridge is zero. However, when an external force is applied on the load cell, the strain gauges will be experiencing different types of forces based on the location, and this will result in the change of the resistance of the strain gauge. Correspondingly, the output of the Wheatstone bridge can be measured, and the magnitude of the output of the Wheatstone bridge is dependent on the magnitude of the force that is applied. This shows how the load cell is set up in the lab. The key component is the load cell assembly. The thin beam carrying all of the 4 strain gauges. The eye bolt used for attaching the wet. Alright, now let's look at the real stuff. The key component of the system, which is the load cell assembly. And the Wheatstone bridge includes 4 wires. 2 of them go to the power supply, that is providing the excitation for the Wheatstone bridge, and the other 2 go to DMM for measurement. This table summarizes the idea of load cell measurement. Different weights will be applied to the load cell, and the output of the Wheatstone bridge will be measured using the DMM. One thing that may be worth mentioning is the output of the Wheatstone bridge is not necessary to be zero when there's no load applied. This is called an offset. If you watch carefully enough, you probably already noticed that the DMM shows 0.4 millivolts in our demo. Let's finish taking the measurements. 100 gram, 0.7 millivolts. 200 gram, 1.8 millivolts. 500 gram, 5.3 millivolts. 1 kilogram, 11.1 millivolts. Those are all of the data points we've been taking in this demo. From this table, we could generate a rough calibration curve. You may make your own calibration curve more accurate by including more data points. In the future, when you use the load cell to take the measurement, all you have to do is to take a DMM. Based on your own calibration curve, you may estimate how much the applied force is.